Welcome to the third part in our series of how to go about creating and discovering exploits. Part of our demonstration piece for our secure coding class. Some of this material is actually taken directly out of that class, demonstrating how it is that vulnerabilities occur and how they can be exploited so that we can better understand how to write secure code. If you're interested in that class, please take a look at the SANS Institute website. You may also be interested in the Security 709 class taught by Steven Sims, one of the best classes I've ever seen for creating exploits, and also he goes into defeating all of the different ways that we have for protecting our applications these days. Address-based randomization, canaries on stacks, all sorts of things. Does a really excellent job of creating exploits and helping you to create exploits to defeat all of those mechanisms. Right now, though, we've just finished completing going through discovering a vulnerability and then determining information about how to go about exploiting it by discovering information about the stack and the instruction pointer and discovering how large the buffer is by using parts of the Metasploit framework. Now we're going to take a look at a very brief tutorial on some shellcode writing, really just an explanation of some shellcode we have here, and then we're going to take a look at how to use that shellcode to manually exploit the vulnerability we've discovered. Let's get started. When you want to write an exploit, after you've discovered how big your buffer is and what kinds of protections might be in place, you're also going to have to take a look at what information you can actually control on the processor. If you've managed to control the instruction pointer, which is the case for us, then you've got a real win. Chances are you've discovered something that you can now create arbitrary code that can be run on this server. In this case, we know that we have a stack overflow, and we also know, well, I didn't go into how, but we know the stack's not randomized. The way we know that is that if we were to run this same attack several times and then look at the core dumps, every one of those core dumps is going to have exactly the same data in it. In other words, the memory addresses do not change. We can also feel fairly certain that there are no stack canaries in place or other protection mechanisms because after we overflow the buffer, we aren't seeing any warnings come up on the console of the server. We've discovered how much space we have. You may remember we had 124 bytes. So with that much space, we've got plenty of room to write an exploit. If we had very, very little room, maybe just a few bytes, what we might do instead is try to redirect execution by perhaps getting the return pointer to return somewhere into the standard library with some parameters on the stack under our control. In our case, we're going to take a look at actually creating some code. For stack-based flaws, the arc injection and return to libc make a lot of sense with protections in place, but shellcode is also very, very easy, especially when you have more than, say, 30 or 40 bytes to work with. To write shellcode, you can start, and I've even seen some tutorials that suggest what you do is you first write some C code and then compile that to assembler and then take a look there and see how you can customize that to create an exploit. That's fine, I guess that's a good place to start, but it's even better to just brush up on your assembler skills. Now don't worry if you're not an assembler programmer because there's plenty of source code out there already, some example shellcode. In fact, the Metasploit project has a huge repository of shellcode available to you, so you could even just start there as a starting point. So what we're going to do is take a look at some example shellcode that we've already written, very simple stuff. We're going to look at it line by line. You can see there's even comments listed over here to help you out in explaining what it does. The very first thing we're going to do here is we're going to, well, let me show you. Here's what it's going to do. This shellcode will run /bin/sh. It's going to call the standard library function for execve using the built-in system call and run a shell. Now, hopefully, we're going to find that we're running as a root user, or even if we're not, just getting some access is going to be very valuable to us. So getting that shell is our first step. So in our code, we begin by moving this value into EAX. Now what does that value represent? Over here I've put in the comments that it's /sh. It's actually not /sh. If you were actually to spell this out, this would be hs/2. Now the 2 is arbitrary. You could put absolutely any value there, the 32. You could replace that with anything. Why are we putting it in that order? And if you look down here, we've got a push that's pushing on another value, an arbitrary value. This is nib/. So if you were to look at this backwards, it's /bin/2sh. why is it slash 2 slash bin 2 slash sh? Why is that 2 in there? When we're writing shellcode, it's very, very important usually to make sure that there are no binary nulls in the code. The reason is most often we're going to find that a lot of our buffer overflows have to do with null terminated byte strings. So if we end up with a null inside of our code is actually going to terminate a string and will probably intercept our own exploit. For that reason, we've instead of writing slash bin slash sh with a null on the end, we've written it with another character, in this case a 32 or the letter 2 on the end, because we can change that value to something else. For instance here, after we move that value into EAX, we then shift EAX right 8 bits. So we had HS/2. When we shift that right 8 bits, we end up with a null moving on the left-hand side, followed by HS/, and the 2 is truncated. It's moved or shifted off of the right-hand side of the register. So while I can't put a null directly in my code, that's a very, very easy way to cheat and simply shift one on. After we've got that value, we push it onto the stack, and then we push the rest of it. So we now have slash bin slash sh with a null sitting on the stack. We move the value of EBX. EBX is going to now contain the stack pointer. So we move that into EBX, and next we zero out EDX. Remember, we can't have zeros that appear here, so by XORing a value against itself, we end up with a 0. With that in place, I can now push a 0 followed by a pointer. Now this seems very arbitrary. Why am I doing that? Well, what I need to do is make sure that my call to the system, the execve, follows whatever parameters it's expecting to find on the call stack. What it's expecting to find is a couple of arrays. One of them, in this case, is going to be this pointer to the slash bin slash sh. The other one is going to be whatever argv contains, which is going to be nothing for us. We could also put arguments there if we wanted to, but we don't need any. So we are simply pushing these things on the stack to set ourselves up as though we were actually calling execve from C, or as though we had taken a C call and compiled it into assembler. So we then push the EDX, we push the 0 onto the stack, we push the pointer onto the stack. Next, we move the stack pointer into ECX, argv is what that's going to represent inside of the call, and move EDX into EAX. That's the 0. So we've now nulled out EAX. Now, why did I do that? Look at the very next line. The very next line moves a byte value into the lower byte of the extended AX register. Here's the reason we've done this. We could have done it in just one line. We could have moved E0x0b into AL. However, or into EAX, excuse me. However, that opcode itself is going to contain nulls. So unfortunately, sometimes when you're writing exploit code, you may need to write it in a you have to kind of circle around to get to your destination, and that's what we've had to do here. I need to put something into the lower portion of AL. EAX is used to list what system call we're calling. You can see the very next thing we do is call the system call, interrupt 80. The value of 11 is the execve call. I need to get an 11 into EAX. I can't use a move for 11 into EAX because I'll end up with 3 null bytes. So instead, I first zero out EAX and then move a single byte into the low order byte of AL. This 2-byte instruction contains no nulls.